Welcome back. So, yesterday we looked into the different performance level. We looked into the performance objective that we are trying to incorporate in our structures. Traditionally, what we do is that we try to incorporate the life safety, that is the paramount objective that we try to incorporate in our design. But here, as we have seen yesterday, we were trying to incorporate the different damage levels associated with the different performance objectives. So, it becomes a multifaceted design approach. So, we will move ahead from yesterday's design and we will look into the multi-hazard objectives. Multi-hazard objectives means that there is a possibility that two types of events or more than two events can occur simultaneously. In case of extreme events, we were dealing with blast event, we were dealing with impact event. There is a high chances that these two events can also occur simultaneously. Blast event on its own will occur when an explosion occurs. Impact occurs when there is a crash, say in the case of an automotive sector. But in case of, let us say, a missile impact, both blast and impact can occur simultaneously. So, here we will be dealing with a multi-hazard scenario. This multi-hazard scenario can again be coupled with different type of natural hazard scenarios also. For example, in case of, it can also occur in conjunction with the wind loading or in conjugation with the earthquake loading, which is an extremely rare event, but still it might happen. So, in today's scenario, we can be faced with a multi-hazard designs. So, the multi-hazard design has its own complexities. So, there is a chances of interaction between a hazard event. What happens is that when, let us say, if a blast occurs or if an impact occurs, so the residual, first of all, one event will occur first. So, the building or the structure is going to perform for this first event, and the residual performance of this structure will be dealt with the other preceding event. Let us say in case of an blast and impact event. There might be conflicting requirements. Let us say for design of impact event, we require high level of localized failure. But in case of other events, let us say for a wind requirement, we may look into the overall performance of the structure. So, there might be conflicting requirements depending upon the stresses, depending upon the displacement or other considerations. So, what we need to do is that we need to follow a integrated design approach, where we are taking into account the responses due to one hazard event and then subsequently the responses due to the other hazard event, and both are trying to be optimized. We need to give a performance based solution. As we have already seen, the structure, depending upon its importance, depending upon its usage, can be classified into different performance categories where different type of damages are allowed. So, depending upon that, we have to design and put a performance based solution. We have to also have a prioritization framework, like which type of events will be given priority, which type of events will have low priority, and the overall serviceability requirement might be fulfilled by one type of event, and the other type of strength based or collapse based might be fulfilled by the other type of hazard event. So, structures must often resist multiple hazards with different characteristics. This is a challenging aspect as far as the design, analysis and the implementation of the facilities go. And there is a high chance that the response of one hazard event might conflict with the other hazard event. So, it requires a careful consideration, designing philosophy, and an integrated solution is always required. Moving ahead, now we are trying to summarize the key design consideration. First of all, we have to have a proactive risk assessment. We have to identify and mitigate the risk at an early stage. If we can do that, well and good. If the risk cannot be mitigated, then we have to look into the design based approach, where we incorporate the remedial measures into our structures. If the structure is already built, we have to retrofit it. If it is a new structure, then we have to incorporate the new philosophies in the structure. So, we have to have an flexibility and an innovation in the design requirements. The limitations of the perspective requirement. We have to have a overall holistic view of our design requirement. We just cannot have a very narrow view and look into just one performance level and expect that all the hazard events meet this performance level only. So we need to have a creative solution beyond whatever we have learned already. So this again opens up a wide plethora of design aspects that have not been dealt with normally in any of the design codes, and we need to have a creative solution, and we need to make our own multi-objective based requirements. Multi-hazard consideration, we have to address the diverse potential risk posed by different type of high risk events. Of course, we have to have the redundancy, where my system should have enough failure path, enough multiple failure path that proves it to be resilient against the single point failure. So we cannot have a single point failure. Always we need to have a different loading paths where the effect of the applied extreme loading can be dissipated. Now we come to the second part. We will introduce the blast loading of on the structures, and we will be looking for the various design approaches that we are going to follow here. Now we are trying to explain what are the different components involved in an explosion. So what we are trying to do here is that we are trying to introduce some terminology that are very much well versed in the blast loading, and we are trying to give a very preliminary overview of the different terminologies so that we are comfortable with it, and subsequently when we go deep dive into the course, we will be explaining it further. So the first thing that comes into mind is a shock wave. Shock wave is a supersonic front characterized by a sudden pressure increase. Let us say we have a balloon and we prick it with a pin. So what will happen is that we will hear a sudden sound. So that sound, if we can visualize that sound, or if we can take a picture of that sound, that will give us a shock wave. So shock wave is the first sudden increase in the pressure front that travels outward from a blast event. Then there is something called a positive phase. Positive phase is the maximum magnitude of the pressure that happens when the pressure increases very rapidly. After the positive phase, there comes the negative phase. Negative phase is nothing but after the sudden increase of the pressure, the surrounding air comes rushing in and fill this positive phase, the gap that is left by this positive phase. So that creates a partial vacuum and it creates a suction effect. So that phenomena we call it as a negative phase duration. After that, we have the thermal effects that are followed. So we have intense heat, we have degradation of the materials due to the thermal effects. So it might be negligible in case of a normal explosion, or it might be very significant in case of the explosion caused by any thermonuclear blast. After that, we characterize the entire thing, the pressure time history, as the area under the pressure time curve, which we call it as the impulse. So this summarizes the total energy that is being imparted to my structure. So if we are looking into the figure, we can see building where we have put a truck in which the explosions have been kept. So we have defined the center of the burst, that is the point where the explosives are kept. The ground shock, there are two shocks, one is transmitted through the ground and one is transmitted through the air. So since this is kept in ground, through the air transformation will be comprising of a hemispherical shock wave, and the standoff distance is the distance from the center of the explosive to wherever we are calculating the pressure. And in the other parts of the building or in the other parts of the structure which is not facing directly towards my explosion, we have the drag effect. So this thing we can visualize in terms of wind loading also, where we have a sudden gust of high intensity pressure flowing into the structure and causing a drag and suction effect. Moving ahead, the different type of characterization of explosions. So explosions can be characterized depending upon where it is being located. So we have internal explosion. So internal explosion we normally deal when explosive is confined within a room or a container, leading to multiple reflections. So whenever an explosion occurs, okay, the pressure will try to move outwards in a very fast manner, but my containment will prevent it from doing so. So it will cause multiple reflections. So what is going to happen is the effect of the total pressure is going to be increased due to this multiple reflections. After that comes the surface burst. In surface burst, the explosives is kept on or near the ground level and where the ground reflections occur. This corresponds to the previous figure that we just saw. So, the previous figure was a case of a surface burst. Air burst, so the above ground explosion is characterized as an air burst, and the dissipation of this burst is over a wide range of area. Moving ahead. So, now we are trying to look into the blast phenomena in a detailed fashion. So, understanding the blast wave characteristics. So, blast wave is characterized by an explosive environment. Okay. So, the explosion will occur in an environment, then the blast wave or the shock front will travel outwards, then we will try to analyze the wave interactions, and depending upon the interaction of the waves with the structure, we will design for the blast resistance structure. In the figure we can see the explosives is kept on the ground. So, it becomes a case of a surface burst. The waves are travelling outwards, and once they hit the structure, the reflection occurs, and then we categorize this as the reflective wave or the reflective pressure. Okay. Next. So, blast load. So, in the figure that we see, this figure is known as a Friedlander's profile. So, whenever we are talking about blast loading, the curve that we use to characterize the blast loading is called a Friedlander's profile. The Friedlander's profile has the following signature. The pressure, that is the overpressure or the pressure signature of the blast itself without any reflection from any surface is called the overpressure. So, the magnitude of the blast loading is defined as the overpressure, that is the highest magnitude of the pressure occurring. It falls into a very short duration. So, the duration from the initiation of the explosion till the positive phase ends, that is very small. It is in terms of milliseconds. Okay. Then after that follows is a rapid decay of the blast pressure phase duration. So, after that the negative phase comes into picture and there is a suction in the overall system. So, the suction pressure might be equal to the overpressure or it might be less than the overpressure, depends upon the material used and the ground condition where the explosion occurs. So, some terms like PSO, that is denoted by the overpressure, TA time of initiation of the blast, T naught positive phase duration, T naught negative, the negative phase durations. So, these are the some of the terminology that we will be using regularly when we are trying to define the blast loading. And this type of profile we normally it is called the Friedlander's profile, and any type of blast loading will be defined in terms of a Friedlander profile having its own value of PSO, T naught and T naught negative. Simplified blast load models. So, what is done in the field is that different types of explosives are taken. For example, TNT based or solid based explosives like TNT are taken, or liquid based explosives are taken, and their whole time versus pressure intensity is being recorded. After recording that, they are being fit into this curve. That is, this curve is known as the Friedlander's profile that we saw in the previous slide, and the corresponding equation is given by this corresponding equation is given here. So, here we try to fit the peak pressure, that is PS, the total positive phase duration and blast waveframe parameter, and the curve fit of this structure is known as the Friedlander's equation, and the corresponding graph is known as the Friedlander's profile. So, in the blast loading we always this simplified model to estimate the pressure and impulse for use in the design methodology. Again, reiterating the key terminologies we have already seen. So, the positive phase duration, that is denoted by T naught, the standoff distance, that is the distance from where the explosion occurs to the distance where we want to calculate our applied pressure. So, that is called the standoff distance. Then impulse, that is the total area of the pressure time curve. Peak overpressure, that is the maximum amount of pressure, that is the signature of the blast event. Reflected pressure is the addition on top of the overpressure caused by the reflections which is being done from the hindrance of any structure or any other obstructions found. Normally, the reflected pressure is greater than the peak overpressure. Reflection effects. So, when a shock wave hits a rigid surface, for example a wall, other type of hindrance, it reflects and magnifies the pressure. So, the reflected pressure is normally always more than the incident pressure or the overpressure. The reflected pressure can be as high as 8 to 10 times than of a free field pressure or the overpressure, especially when this thing is done at a perpendicular distance. So, the angle of incidence also affect the reflected loading. So, the reflected impulse is also significantly higher than the impulse that is we derive from the overpressure signature. So, here in the graph we can see the addition of the reflected pressure also. So, PSO we have already seen is the overpressure and PR is the reflected pressure, and as the signature says, the magnitude of PR is significantly greater than PSO. In blast engineering, what we do is we use something called a scaling law. To understand the scaling law, we need to understand one thing. The amount of pressure that happens at a given point is a function of the total amount of charge, that is the total amount of equivalent mass of the charge or equivalent mass of the explosive, that is always expressed in terms of TNT equivalent. So, though the unit is kg, it is always expressed in terms of TNT equivalent, meaning it is scaled in terms of the total energy released due to 1 kg of TNT. So, there are different types of explosives used. So, the standard unit of the explosives is TNT equivalent kg. So, the amount of pressure that occurs at a particular point is a function of the W, that is the explosive mass, and the distance between the center of the explosive to wherever we are calculating the pressure. So, it might happen that if I use a very large amount of explosive mass, but my distance is also very great. So, the net effect of the pressure will be, let us say it is 1 unit, but if I use less amount of explosive, but also I reduce my distance. So, again the net effect of the pressure might again be 1 unit. So, the amount of charge and the distance, both of them has played a crucial role here. So, they are both in both the scenarios having high charge and large distance, and low charge and small distance are giving me the same effect. So, this phenomena we use to scale our total amount of blast. So, we use something called a scaling factor, where scaling factor is directly proportional to the distance from the explosive to the target and inversely proportional to the cube of my total amount of explosive. So, two explosives are dynamically equivalent if the scale distances mentioned z are the same, meaning both of them will give me the same effect in terms of pressure. This scaling law is one of the most widely used tool in the blast analysis, and it is also used to characterize the different types of explosives also. And here also we can equivalent the amount of kg of TNT and get the TNT equivalent also. So, this is a very crucial phenomena that we need to remember and we need to incorporate whenever we are trying to calculate the net effect of the blast on a given point. So, how is blast load different from any other loading? In any other loading, the effect of the loading transferred to the structure is very slow. So, there is a delayed structural response. It might happen that my structure is behaving in a very sluggish way, and there is also a gradual change in the loading. So, it comprises of different types of loading normally assessed like earthquake loading or wind loading. But in terms of a blast loading, the effect of the loading is very high. It comprises of a very high magnitude, and the total response time of the structure is very less. There is an immediate structural response, and there is a rapid load deployment on the structure also. So, blast is not a constant or slow varying load like wind load, live load or an earthquake load, and it has the signature of an impulsively applied loading, meaning that loading occurs faster than the structure can respond to it. What factors influence blast load severity? So, blast load, as we have seen earlier in the scaling law, blast load is affected by the charge weight, that is the amount of explosives More the explosive, higher pressure and the higher impulse. It is also affected by standoff distance, that is the distance from the explosive to the target or wherever we are calculating the pressure. So, larger the distance, the blast intensity is considerably reduced, and it is reduced exponentially. Confinement has to do with the reflections. So, even if we have a low overpressure as a signature of the blast, due to the confinement effect, the PR, that is the reflected pressure, might be significantly high, and it can be as high as 8 to 10 times. So, there is an amplification of the pressure here. Surface reflections, there might be reflections from the ground, there might be reflections from the other sources, thereby increasing the effect of the pressure loading. The medium in which it is traveling, so the intensity of the blast wave is also affected by medium where it is occurring. So, air, water or structure can significantly change the shock wave behavior. So, the structural response to blast. So, the structure is always characterized by its three signatures, that is the stiffness, mass and ductility. Blast is characterized by its signature of pressure and impulse, and both of the things when they are combined. So, blast is the external application of the load and structural properties are the internal resistive mechanism. So, when both of them combines, then we have the structural responses, and these structural responses are also affected by the shape of the structure, the boundary conditions, the material applied, and then we try to measure the response of the structure in terms of deformation, in terms of stresses, in terms of shear forces, and then we try to design these structures. So, there might be some energy absorbing materials also which are used to mitigate the effect of the blast. So, if the structure is able to deform and returns to its original shape, then we can use the property of elastic deformation. We can use the property of the plastic deformation, where even if the structure is deforming permanently, but it is absorbing significant energy. So, we can use a sacrificial element. Let us say we have a structure, a box type of building to protect. So, we can put some cladding, where when the extreme event occurs, the cladding absorbs all the energy, it has a permanent deformation, but then we can replace it with a new cladding, and the structure is not affected by my application of the external blast. It also might happen that there is a damage or incipient failure in my structure. So, the structure might dissipate, it might collapse, but it has served its purpose. So, these are the modes where we can use for the blast energy absorption. Damage mechanism in the structure due to blast. So, we will look into the different damage mechanisms that occur in the structure when a blast occurs. So, we might have connection failures, that is the connection between the beam column joints or connections between the different steel members in a truss or different members in a precast system is broken down. We have a bending failure. So, for a bending type of structure like beams, slabs, they fail in my bending mechanism. We will have shear failure. So, in walls and connections, we might see shear failure. There might be a case of a progressive collapse. So, progressive collapse can be used in both ways. Progressive collapse can be used in a positive way, where we have to dismantle a structure, and it can be used in a destructive way also, where intentionally some structures needs to be broken down. So, progressive collapse is nothing but a chain reaction of failures leading to the total collapse of the structure. Then we can also have uplift and fracture. So, there might be a sudden damage in the structural component leading towards the upward application of the forces and the bending moments. Spalling is often characterized by the concrete, the surface concrete breaks up due to the formation of the high pressure zone, and it's tried to shed off. So, spalling is the most common phenomena that we can see during a blast or an impact event. So, damages often begins with high stress concentrations, and it is our job through this course to teach how each element fails in this type of blast or impact loading, and how we can improve it, how we can restrict it, and how we can improve the ductility behavior, and how we can incorporate the redundancy in the design, so that this type of failures are either minimized or they are totally prevented. We talked about the structural components, but in many buildings, many lifeline structures, there are non-structural components also, and they often are very much vital to the functioning of that particular structure. For example, in hospitals, we will have the machinery which is operating machinery, diagnostic machinery, which are very much critical for the functioning of the hospitals. In data centers, we will have servers. In electrical installations, we will have the transformers and all, which are very critical for the functioning of these structures. So these non-structural elements can pose two types of hazard. One hazard is that they form a loose element and they are going to have a secondary effect on my parent structure. Second thing is that these non-structural components receives a failure in themselves. So if this non-structural component fails, which are very vital to the functioning of my installations, then the whole purpose of saving this structure is defeated. So in addition to designing for the protection of the primary structural elements, we also need to design for the non-structural components, so that the hazard posed by the non-structural components is minimized, as well as there is no failure or minimal failure in the non-structural components as well. So we'll look into different type of non-structural elements, like for windows and glazing, they will form a hazard in form of flying glasses. So the mitigation effect can be, we laminate the glasses. HVAC systems can explode in themselves, and it might lead to the spread of this blast effect. So mitigation methodology can incorporate like backflow prevention. Other components like elevators, ceiling lights, light fixtures, they might prove as a secondary hazard, where they itself becomes impact type of body or a blasting type of body and affect my primary structural element. So we need to properly anchor them. Other type of equipments might act as a projectiles. So again, anchoring is requirement. So we have to look into the primary structural elements also, and we have to look into the non-structural components also, so that we protect them as well as we prevent them from becoming a secondary hazard. So even when the structure survives, and non-structural element can cause serious injuries and functional failures. So injuries to the person and the functional failure to the overall system has to be mitigated. So blast protection is a scenario where we must extend beyond these core structure components to equipment, finishes and fixtures. So this transforms into a holistic design method, where we look into the each and every aspect, we analyze them, and then we design so that our primary as well as the secondary structural components survive the effect. So we again are trying to summarize the design challenges in the blast engineering. First and foremost, our load is a highly uncertain event. The occurrence of this event is extremely rare. When it occurs, the magnitude of the pressure and the time duration is very less. So we will always have a scenario where we do not know what amount of charge or weight or what is the standoff distance, because we cannot predict where the third party is going to put the missile, what will be the payload of the missile, and at what precise location he is going to hit. So we will always have to design for a very conservative scenario. So the design becomes very heavy whenever, due to the uncertainty involved in the loading parameters. The behavior of the structure. In most of the cases, our structure will go into the nonlinear behavior, where plastic deformation occurs, local failure occurs. So due to the uncertainty in the loading and the non-linear behavior associated with my structure, the cost will increase tremendously. So we will have to establish a cost versus protection trade-off. So due to our constrained budgets, we will have to a trade-off between how much level of protection we want to achieve versus how much cost is involved. So here the performance-based engineering comes into picture, where we can categorize each and every structure depending upon their performance, depending upon their objective, depending upon their importance, and we can achieve a cost versus protection trade-off. The behavior of the material will also change, because it is a highly strained events. So the material will become very stiff in itself, but it will lose ductility. So the behavior of the materials like concrete and steel are very different from a normal event. Then after, if we cannot prevent the scenarios, we will have to have some retrofitting measures here also. So again, depending upon the cost, we have a retrofitting limitations. There might be two cases where we have an existing building which we need to retrofit against any blast threat. So they might themselves have some limitations due to the amount of detailing that has already gone into the existing building, or we might face a scenario in which a newly designed building has been destroyed by an event that we have not designed. The event was more than the expected event and we need to retrofit that structure. So again, the cost versus protection trade-off comes into picture. So we'll stop here and we'll resume from the next class.